Bonjour, Jerry. Ah, comment tu vas? Ça va, super. Merci beaucoup, merci. Ouais, ok, non, pas de souci. Pas de souci. Merci, merci. Bah là, j'ai vu qu'on t'a fait patienter dans la salle d'attente. Je voulais que ça fasse passer automatiquement les gens. Je vais... Allô? Oui, oui, je t'écoute.
je suis là.
Bon, ben, très bien. Ah, toi aussi, t'as ça dans ça.
Ouais, c'est moi.
Bon, ben, très bien.
Ouais.
Je n'allais pas fermer.
Coucou.
Salut.
Ça commence à quelle heure?
À 14h.
Ok, super, c'est où là?
C'est ici.
Ok, 14h.
Ok.
Allez, bon courage.
Merci.
On va voir si le son il passe sur YouTube.
Bon, ça va démarrer à 14 heures. We are going to start at 2 p.m. Ariel.
Ah, moi je t'ai dit que je ne peux pas laisser mon élément comme ça. Ça comment?
Ça va.
Mais le mieux ça arrive, il connaît. Il faut que tu sens que tu soutiens. Qu'est-ce que c'est l'histoire ça? Moi tu crois que moi-même depuis là.
Ouais, mais j'ai pas regardé.
Non,
Parce
en
que
fait.
je suivais des gens qui se connectent à distance.
Oh, il y a combien de personnes?
Il y a que dire, mais les gens ils se connectent à leur pays, quoi.
Ah,
Ils ne se connectent pas.
Ouais. Il y a que les jurys actuellement.
Ils sont même pas encore là. Moi, je suis connecté pile 14h, quoi.
Ah, donc le jury, tu vas parler avec le jury à distance?
Il y a 2 qui sont en présentiel et les autres sont à distanciel.
Ah, c'est ton document, hein?
Ouais.
C'est ça même. C'est chaud.
Ça va?
Il n'y a pas beaucoup que je dis. Et il a dit que comme il a posé des jeux, il t'avait dit ça. Donc du coup, il a dit que non. Il dit qu'il ne faut pas qu'il vienne seulement venir dans sur place.
Ouais.
C'est des risques, mais tu es à quel niveau?
Tu te mets où tu veux et tu te.
Ouais.
Là, sur le jury, tu peux te mettre par.
Oui.
Plutôt se mettre
D'abord, oui, parce qu'il ne faut pas qu'on voit. Effectivement, je vais me mettre aussi derrière. Surtout que c'est même bien ta salle. Parce que puis, je suis monté, je tourne. Oh, mais c'est bien, tu fais que tourner, tu te mets. Je vais dire, mais si elle rentre et tout, c'est mal. Pour qu'elle s'embrouille pas.
Demande dès que tu rentres, tu demandes ça du conseil.
Ah, c'est on dit ça du conseil,
Ouais,
c'est bien.
à 102.
Oui, parce que moi, il n'a même dit c'est tourné étage.
Ouais.
Parce que tu allais se partir comme ça, j'ai vu le vois B. D'abord, tu sais qu'Eddie avait soutenu là, ici à côté.
Ah,
Tu vois, quand tu montes les salaires à gauche, vers A11, A12. Oui. Et Eddie avait soutenu par là-bas, le couloir de l'autre côté. Du coup, quand je trouve, je dis, mais on a dit, ah, c'est ça.
Bonjour.
C'est ici pour la toute, non?
Ouais, c'est ici.
D'accord. C'est vous qui.
Ouais, c'est moi.
Parfait.
Du coup, vous installez là.
Bonjour.
Ça va démarrer à 14h.
Ouais, on n'avait pas parce qu'on est déjà en retard, on fait du bruit dedans.
Ouais, non, c'est bien comme ça. Comme ça, au moins, on est tranquille.
Oui, voilà. Bon, il n'y a pas. Il y a comme ça. Ah, oui, là. D'accord.
Ouais, je crois que c'est.
Ils sont encore arrivés?
Non, ils ne sont pas encore là. Je crois qu'ils vont. Ils doivent un peu décider qui sera le président du jury, quelque chose comme ça.
Ah. Faut que ce soit absolument un examinateur ou ça peut être.
Non, ça peut pas être. Ça peut pas être.
Non, non, parce que vu que.
Ça peut être un rapporteur, mais ça doit être un des examinateurs.
Je veux dire, ça peut pas être Méfou par exemple.
Non, ça
parce
peut
que
pas.
du coup, il est. Alors, c'est pour ça qu'on soit examinateur du coup. Ah, ok. Ça sera un peu la triche.
Attends, je vais me faire.
Quoi?
Viens. Ça, c'est les clés du bureau.
Ok. Ok, du coup, en fait, c'est pour le scooter qui arrive à 16h, c'est ça?
Ouais, et je peux récupérer les trucs si c'est nécessaire.
Ok, donc du coup, il passe à ton bureau à 16h ou tu
Non, je sais pas. En fait, ils vont m'appeler par
Ouais.
mon téléphone, tu décroches
Ok.
et tu vas dire où ils vont être installés.
Ok, ils vont. Donc du coup,
Ils vont installer dans
à
à
5
5 voilà.
Ok, ça marche.
Du coup, le bureau, c'est pour prendre les autres côtés qui sont là-bas.
Les autres, ok, ça marche.
Tu vois? Et tu auras besoin d'un téléphone.
Comment?
Peut-être tu auras besoin d'un
Ouais, de toute façon, si les scooters sont là, ils vont m'aider aussi à. T'es bien habillée. Du coup, c'est quel est le meilleur endroit pour prendre des photos?
C'est pas la photo, tu fais tout ça.
Mais Franklin, dis-moi, excuse-moi, c'est mieux quelque chose à quelle arène
Je sais pas.
en plus,
Oui, je crois que mieux campus, c'est meilleur. C'est à peu près pareil.
c'est pareil, non?
Ouais.
Les deux, c'est pareil.
Ouais. Peut-être mieux campus, là, c'est plus. Là, elle verra directement des images écrites sur le.
Dans les lycées, c'est pareil campus. Ok, je vais dire ça.
Déjà, je vais en profiter pour prendre mon photo là maintenant.
Ah, ok.
Bah, avec les titres.
Ah oui, c'est même vrai. Ok, comme ça, avant qu'on commence, oui, qu'on a la possibilité. Excusez-moi. Merci.
Bonjour.
Voilà.
Ah.
Voilà. D'accord. Mais comment te fouilles dans ton document? Tu peux donner cours un motif. On peut commencer.
Je vais donner cours pendant les 2 premières années.
Non, c'est bon, c'est bon. Il faut qu'on te laisse tout long. Maintenant, tu concentres. C'est bien les documents.
J'ai une question. Est-ce que tu sais à peu près combien de temps ça va durer? Parce que je suis intéressé, mais j'en ai plus 15 heures.
15 heures? Ouais, attends. 15 heures, je crois que la soutenance sera finie. Mais la question réponse, ça sera pas fini. Parce que c'est 45 minutes de soutenance. Si on démarre à 14h, à 14h45, j'ai fini de présenter. Et après, il y a une séance de questions-réponses.
Ouais.
qui peut durer 1 heure comme ça peut durer 2 heures.
Ouais.
Ou 3.
Ou 3 heures.
Ah,
Jusqu'à moi.
J'ai déjà vu, mais c'est parce que plus que 3 heures de questions.
après, il n'y a pas de souci, il y aura l'enregistrement sur le lien YouTube.
Oui, il y a beaucoup de gens qui
C'était une thèse, il y avait.
Oui, c'est vrai que moi j'ai pas le rendez-vous, mais j'ai quand même des révisions pour demain.
Ouais, ce serait peut-être plus malin de juste se connecter au chat Teams. En fait. On n'est pas loin en plus, donc on est pas arrivé début.
Longue question qui s'écoute un peu parler.
Ouais, c'est là au moins pour la ça fait pour la question à la limite.
Ouais, c'est
Ouais,
vrai que
ça,
ça,
c'est
j'allais pousser un peu.
Pour qu'il parlait.
Voilà, en tout cas, j'aimerais au moins que vous ayez fini votre code.
Non, si vous pouvez pas.
Après l'an
Vous
prochain.
pouvez rester écouter et vous partez vous connecter sur
Voir
Teams.
aussi un peu ça.
Surtout, oui, c'est vrai. Du coup, si toi tu t'en vas, les deux intéressés par la recherche sont déjà pas là. C'est vraiment.
Toi, tu n'étais pas intéressé.
Oui, mais moi, c'est le sujet qui m'intéresse.
Et tu finiras par nous rejoindre. Après master. Tu finiras par nous rejoindre.
Peut-être. Si jamais j'ai rien et que cela là me prend, bah oui.
Une tactique pour pas trop gêner, pour pas voir faire ça, je vais plutôt m'asseoir par là.
On a ça.
Comme ça, on gênera,
Mais après ça y est,
Ouais,
moi je veux. Mais c'est que c'était la recherche. Il y a une plus-value. Et aussi le fait que quand tu prononces les réponses, tu es content. Tu dis que je suis populaire. Mettez le nom là. On voit que téléphone. Ça, moi j'aime bien ça. C'est pour ça qu'il y a des débats souvent, ça va dans les écoles. C'est la réponse. Tu es tranquille.
Ah, salut Philippe. Ah, merci. Ça va? Ouais, ça va. En forme. Ouais.
Ah, vous êtes passé? Ah, non, pas moi.
Non, il y a pas de moi, j'essaie de répondre bien pour les photos. C'est un peu loin. En fait, ça, on est sur ça. Moi, dès ça, je suis dedans. Après, ce que je vais faire ici, c'est peut-être le refaire.
Ah oui, le refus de la journée, ça va être super bien.
Ah oui, voilà, c'était là.
Ah oui, si, c'est bien. Ouais,
Il y a autre chose pour
Est-ce que tu vois mieux impeccable?
Ça va, c'est bien remédier.
Ouais.
En fait, je suis un
Ils ont posé des journées avec tous les spécialistes.
Et après, il faut que je fasse une plus des autres. Alors, ça, c'est un truc qui est plus, c'est pour farm, la partie pour acheter quelque chose. Ouais, j'ai le passeport de finir. Pour personnel, ça va. Et pour le Vespail aussi, j'ai réussi à empêcher un truc pour les fantaisies. Et pour le Symphonia, j'en ai pas. Les armes, des gens, évidemment, mais les armes, merde. Et ensuite, on peut plus foutre d'acheter un truc qui va coûter ces armes de merde.
Je crois que je vais me chercher. J'étais sûre que je Merci.
Ok, bon.
Merci. Merci.
Hello, sir. Can you hear me? Good, thank you. Hello, Elisa. Hello, Tony. Hello, Sébastien. It's nice to see you too. It would have been a great pleasure to have you here physically as well. Yeah, it's on, I understand. Okay. So we are just waiting for Engelbert and David. Oh, yeah.
Il va manquer tennis, non?
Il est là. Il est ici.
Je me place comme ça. J'ai plus de téléphone.
Can you see us all? And can you hear us now? It's okay for you? Distantly? Great. Okay, so we will start with a short presentation of the PhD board. First, we have Professor Anthony Bagnal from the University of East Anglia in UK. Then we have Sébastien Deskerk from the University of Technology de Compiègne, Research Director, and also another professor from the University of Rennes, Elisa Froment. Then we have Professor Thémis Palpanas from Institut Universitaire de France, also Paris Cité, also, I think. And then we have Emmanuel Gangler, Research Director, not present here because he's sick. And we have, as the Director of Michael thesis, we've got Professor Angelbert Nguifo, and myself, Professor Hill, and I will chair this PhD board. Then Michael, you can start if you want.
Thank you, sir. Let me just this slide. Can you see this slide? Okay, thank you. Okay, thank you, Mr. President. Thank you to all the members of the jury. Thank you to the guests. I'm very happy today to present you what I've been doing since 3 years now. And this project is entitled Explainable Classification of Uncertain Time Series. And it has been supervised by Professor Engelbert Nguifo and funded by the French Ministry of Higher Education, Innovation and Research. Now, before I start, let me give you some situations where we need to deal with uncertainty. So the first one here is in the domain of astrophysics, where we have ground-based telescopes which are built on Earth in order to observe the space. And between the telescope and the space, we have many obstacles. We have the cloud, the atmosphere, we have the air, etc. As a consequence to this, the collected data are uncertain. And this is due to the environment in which we are doing our measurement. Another situation is something that happened recently in one of the French territory when violent storms hit Corsica, though the alerting system did not trigger at time. And this actually killed 2 people. I think they updated the number of deaths, but at least it killed people. And a forecaster at Meteo France, the French institution on the weather forecasting, said the day before yesterday, there was an arrow model which predicted strongest at the level of Corsica. But in our rationality, we have preferred to take a more reasonable scenario. So here, we see many things. We see that there are uncertainty due to the fact that modeling storms is extremely difficult. And we also have uncertainty coming from the forecasting model, which is here, the arrow model, as they call it. And you also have uncertainty due to the subjectivity of the operator, the man behind the computer program. So these are only 2 examples of situations where we need to deal with uncertainty. But there are many such examples that we can come up with. So my research project is framed behind 3 questions. The first one is, how can we learn from uncertain data? That's the first question. The second one is, can we improve model performance by taking into account the uncertainty of the data? And if we manage to learn from this data and we manage to improve our model performance, can we even trust the insight that we got from this uncertain data? So this is the outline of my presentation. I will start by giving a brief introduction of the research thesis. I will give some background where I will define some notions that I will use during the presentation. And I will present our 2 main contributions. These are the UST model and the USAS model. Then I will conclude. So let's start with the introduction. So first, we are facing what is called the machine learning revolution. Because machine learning is literally affecting every aspect of human life. And this, for instance, we have machine learning used in medicine to discover new drugs. We have machine learning used in transportation in order to optimize the way we move. And we also have machine learning used in physics in order to understand the universe in which we live. And this is possible because of 3 main reasons. The first one is that we have a huge volume of data that is now available. This is tabular, video, audio, or time series data, and I will focus in this project on time series data. The second reason is that we have optimized algorithms that have been built by researcher and engineer to extract useful information from this data. For instance, we have deep learning, and we have also an increasing computing power. We have more powerful CPU, more powerful GPU. We even have a new type of processing unit like TPU, tensor processing unit, and we also have the cloud infrastructure that have been built to facilitate the access to all these new technologies. So what is machine learning? In a classical programming framework, we used to input to our program the data and the rules, and the program will apply the rules on the data and output some answers. With machine learning, the process is a little different, as we input to the program the data and the answers, and we let the program learn the rules from these data. And this is good because the program is even able to learn rules that were unexpected by the human. And what about time series? So a time series is a type of data that is used to model the evolution of a variable over time. And it can be univariate, like here we have the evolution of daily new COVID-19 case in Africa from the 18 February 2020 to the 19 April 2022. And here we have a single variable, which is the number of COVID-19 cases per day. It can also be multivariate, as here, where I was doing the Taekwondo run ross kick, also called bandal chagi in Korean. And here I was tracking the location, so the x-axis and the y-axis of my right ankle while performing the kicks. So here we have a bivariate time series. Now, what about uncertainty? So any measurement is subject to uncertainty, and this is due to many sources, like the environment in which we are doing the measurement, like I said with astrophysics. We also have the precision of the sensor we are using to make the measurements, and we have privacy preservation. This is a situation where data provider hides some part of their data in order to preserve either the privacy of the data or the privacy of their customer. And unlike error, which can be removed by being careful, with uncertainty we cannot remove it. We can only reduce it to a certain level, but we cannot eliminate uncertainty. So this is why there are a lot of communities working on this topic. We have, for instance, the SIPTA community, which focus on imprecise probability. We also have the Association for Uncertainty in Artificial Intelligence, which is a top-ranked conference. And we also have a lot of workshops at international conference on uncertainty in machine learning. Uncertainty can be categorized using this taxonomy if the uncertainty is due to some missing information, some missing knowledge, or some lack of knowledge. We talk about epistemic uncertainty. And under epistemic uncertainty, we have incompletion, which is the case where we have missing information on a situation. For instance, an example that is really common in machine learning is missing data in a dataset. We also have imprecision, which is a situation where we have an information that is not precise. I will give an example to show this. Instead of having the age of someone like 20 years old, you have an interval like between 18 and 19. So you are not sure what is the exact age of that person. Another type of epistemic uncertainty is unreliability, when you record data from uncertain sources or from unreliable sources. Now, if the uncertainty is not due to lack of knowledge, we talk about aleatoric uncertainty. And a particular case is the random seed that is used in many computer algorithms. So in this work, I'm going to focus on imprecision. And although I will use the word uncertainty during the presentation, keep in mind that I'm talking about imprecision. Now, I'll give a brief word about explainability. So explainability is a set of tools that is used to understand a model, to trust a model, or to debug a model. And a typical way of doing this is to find the most important features used by the model to take the decision. And in the case of time series, we have here a classification case where we have two classes. These are different types of arrow, and we can find in red the region on which the machine learning algorithm focus the most in order to distinguish between
these two type of arrows. Now, there's a great debate in the literature about the difference between explainability and interpretability, but in this work, I'm not going to focus on this. I will assume that they are meaning the same thing, but this is a debate in the literature, so I'm not going to deep dive on this subject. Okay, now I can give the thesis objectives. So the objectives of this thesis are twofold, but before I give the objective, you have to keep in mind that time series classification is the most applied and studied, so one of the most applied and studied time series analysis tasks. And there are many papers published on time series classification in the literature with very good performance. And very few papers have been published in the case where we have uncertain time series. So the first goal, which is also the main goal of this thesis, is to advance the state of the art of uncertain time series classification by building models that are effective, in that sense that they should do what they have been designed for. They should be robust, because we want our model to be effective even in the case of high uncertainty. And we also want our models to be explainable, so they can be easily adopted by domain experts. The second goal of this thesis is to see uncertainty not as a problem, not as a difficulty, but as an additional input that can be used to make better decisions. So now the background. So I will give a formal definition of a time series and of an uncertain time series. So a time series of length m here is a sequence of ordered, it's an ordered sequence of real value. So here you have t from t1 to tn, and all ti belongs to r. Now, if we have our ti being uncertain, then we have uncertain time series, and we define two ways of modeling uncertainty. The first way is to use the multi-set based model, where each ti in our time series is represented by a set of possible value. The second way is to use the probability density function based model, where each ti is represented by two values, a best estimate, which is ti hat, and an uncertainty, which is the standard deviation, and here it is delta ti. So here's an illustration of an uncertain time series, and you can see that at each time step we have on each dot a red vertical bar representing the fact that the dot could be anywhere on this bar, but we use the best estimate to have the best estimate of our uncertain time series. Now in this work I will use the probability density based function as our uncertainty modeling, because the multi-set based representation is costly to manage in terms of computation time. Now, when we have to analyze uncertain time series, generally we don't work on the whole time series. We are going to use some pattern in the time series that are called subsequences. And this is only a set of consecutive value from a time series. Here I call it S, and its length is L. We also define the notion of distance, which is used to compute the similarity between a subsequence and a time series. Note here that there's a difference between the gist with a capital G and the gist with lowercase d. And the lowercase gist is used to compute the similarity between two subsequences of same length. So here L, and the gist with capital D is used to compute the similarity between a subsequence and a time series. And this is actually the minimum distance between the subsequence S and any other subsequence of the same length in the time series T. We also have the notion of separator, which is a subsequence that is used to divide a dataset of time series into groups. For instance, a special type of separator which is highly interesting in time series analysis is shapelet. And this is a separator that maximizes the information gain. Here we have, for instance, a dataset of two classes of time series. We have the blue and the red. And we want to find a subsequence that is close to one of the group and not to the other. And here you have one that we have extracted from the dataset. And we see that this subsequence can be used to divide the dataset in two groups that are homogeneous. And if the subsequence is similar to a time series, it follows the yes path, and we have the blue time series. Otherwise, it follows the no path, and we have the red time series. And this is a perfect shapelet. And this is a feature that we are going to use in this work because they are interpretable in that sense that we are always able to affect this to domain knowledge, this shapelet to domain knowledge. Perfect. Now, the state of the art of time series classification can be summarized using this figure that I proposed. So the first step is going to be feature extraction, where we are going to extract a set of k features from the time series. And then we are going to perform a feature transformation, which consists of replacing each time series in our dataset by the vector of its features value. So either this feature a shapelet or back of word or neural network weight. Anyway, and then we can then apply any supervised classifier on the transformed dataset in order to have the classes. In the literature, there are some methods like the legacy first nearest neighbor combined with dynamic time mapping. We also have the shapelet transform classification. We have IFCode, which is a meta-ensemble model. We have Rocket, which use random convolution in order to extract features from the time series. And we have TST, which is a meta-tree ensemble. Also, we have XCM, which has been proposed recently, and it's also based on tree and combined boosting and bagging in order to increase the performance of the classification, and also provide tools to do explainability. In this work, I'm going to focus on the shapelet transform classification because it offers interpretability capability, and this is a property we want to have in our model in order to facilitate their adoption by end users. Now, concerning uncertain time series classification, there are not real methods in the literature, at least when we started this thesis, that focus on the classification of uncertain time series. But we have uncertain similarity measures that are generally used with combination of the first nearest neighbor in order to perform classification of uncertain time series. For instance, we have FOTS, we have DUST, we have MINIC, and we have PROUD. The problem with all these measures is that it doesn't provide the uncertainty on the similarity. It means that if you compute the similarity between two uncertain time series with a MINIC or with FOTS, the result that you obtain is a real number. And on this real number, you don't know what is the uncertainty on this similarity. And we think that this is not good because the uncertainty disappears brutally during the process. So what I mean is that after the feature extraction using an uncertain similarity measure, the feature that we extract do not have uncertainties. It means that the remaining part of the process is not aware of the fact that the input data were uncertain. And we think that this is not good for such a model, or at least this should be improved. Okay, now I'm going to present the first contribution, which is the uncertain shapelet transform model. And this actually is what we use to let's say to fix the problem of uncertainty brutally disappearing during the process. So before that, we propose this general approach, this general design of uncertain time series classification. We think that the first step should be an uncertain feature extraction, meaning that the features that we are going to obtain after this step will have their associated uncertainty. And then we are going to perform an uncertain feature transform, like with the time series classification without uncertainty, and we'll obtain a tabular data with features value for each time series with their associated uncertainty. Then we can use an uncertain supervised classifier to perform the classification and obtain uncertain classes at the end. So this is what we think should be the ideal way of performing time series classification when our time series data are uncertain. So this is good because uncertainty doesn't disappear anymore, but it is propagated from the beginning to the end of the process. Also, this approach looks more intuitive and therefore more trustable by end users. But how do we propagate uncertainty from the beginning to the end of the process? So let's say we have two uncertain measures x and y, which are defined by x equal x hat plus delta x and y equal y hat plus delta y. We have formula defined in the literature to compute, or at least to do arithmetics on this value. We can compute the summation of these two values, and we see that the best estimate are added together, and the uncertainty are also added together. We also have formula for the subtraction, the multiplication, and the division. And in any case, we see that the uncertainty keep increasing when we do arithmetic on uncertain measure. Okay, now in time series analysis, especially in classification, Euclidean distance is generally used to extract features. And in practice, we use the square Euclidean distance. So this is why you don't have the square root on this formula. If we apply the uncertainty arithmetics that I've defined just before on this distance, we obtain what we call the uncertain Euclidean distance. And this actually gives us not only the similarity or the best estimate of the similarity between our two uncertain time series, but also an uncertainty on this best estimate. And this is interesting because UED is simple to compute as it has a linear time complexity, similarly to Euclidean distance. Then another thing that is generally done when performing time series analysis is that we are not going to compare the subsequents as they are. Generally, we are going to normalize the subsequents in order to put them on the same scale so that the comparison is scale invariant. And how do we normalize uncertain subsequents? This is what we do. The first step is to convert uncertainties to relatives by dividing each uncertainty by the corresponding best estimate. Then we are going to normalize the best estimate by subtracting the means of the best estimate in the subsequent and dividing by the standard deviation of the best estimate in the subsequent. Then we are going to reconvert our uncertainties to absolute by multiplying the normalized best estimate by the relative uncertainty. This is how we normalize our uncertain subsequents. Then another question remains. We want to compute the similarity between a subsequent and a time series, and this is defined using a minimum function. How do we compute the minimum of a set of uncertain value? So what we do here, we define two properties. The first one is the equality property, which actually tells us when two uncertain measures are equal, and this is the case when they have the same best estimate and the same uncertainty. Now the inferiority property is used to define when x is smaller than y, and this is the case if either the best estimate of x is smaller than the best estimate of y, or they have the same best estimate but the standard deviation or the uncertainty of x is smaller than the uncertainty of y. This property is interesting for us because we know that the best estimate are generally given by domain experts. So we want to put more trust on this value than any other value, any other possible value of the uncertain measures. Although these properties are too restrictive, they are actually a good starting point to deal with the uncertain measure. Now we can define our uncertain Chaplet transform algorithm. The process is this is an instantiation of the general design that we proposed at the beginning. So given a 20 set of uncertain time series, here I use only two classes, but we can have more than two. The first step is going to do a Chaplet selection. So here we are going to extract Chaplets, which are actually subsequences with their uncertainties, and this is done by generating all the subsequents from our time series. Then for each one, compute the information gain and sort the subsequent by their information gain and take the top one. Then we are going to perform our uncertain Chaplet transform using the uncertain Euclidean distance and obtain an uncertain transform data. And the next step is going to be the standard normalization, because this step is really important as the uncertainty keep increase when we perform arithmetic on uncertain measures. We need to do this step in order to have the uncertainty and the best estimate on the same scale. Then we can perform the classification using a supervised classifier. Okay, to evaluate this method, we use 15 datasets, which we call Chaplet datasets. These are datasets on which Chaplet methods are known to work well. And on this dataset, we added random uncertainties, and we consider two levels of uncertainties. The first one is the low uncertainty level, where we have very few uncertainty added in the data, and we have the high uncertainty level, where we have more uncertainty that have been added in our dataset. This is to see how our model will react when we increase the level of uncertainty. So to show the performance of our method, we use the critical difference diagrams, which is used to show if there is any significant statistical difference between a set of models trained on a set of classifiers. And here we consider the models here are actually different configuration of our model. The first one is the UST model using the uncertain Euclidean distance, and the uncertain Gaussian naive Bayes, which is a model built to an adaptation of naive Bayes classifier to uncertain tabular data. And the second model here is the uncertain is UST with UEG and GNB. This is to see how different are the results when we propagate uncertainty, then use an uncertain supervised classifier, compared to the situation where we propagate uncertainty, but we use a classifier that is not uncertain. And then we also have UST using the uncertain similarity measures defined in the state of the art, like thought and dust. Here, ST is UST using Euclidean distance and GNB. We call it ST just for simplicity because this is similar to the shapelet transform classification, even if you are not using the same classifier that have been used in the original paper. And here, if you have a bulk bar connecting two models, it means that they are not significantly different. Otherwise, they are significantly different. And here, we can see that propagating uncertainty and use an uncertain Gaussian naive Bayes is better than any other configuration. And we can also see that our proposed method is better than using the existing uncertain similarity measure, which are all on the right part of the figure. Now, if we increase the uncertainty, this is what we see. The observation is that here we have the performance of ST model degrading after increasing the uncertainty, and we think that this is because ST is not actually taking uncertainty into account, while our model stay at the first place of the ranking. So we see that here propagating uncertainty, then use an uncertain supervised classifier is better to perform classification. So at least we are able to improve the performance of the classification by taking uncertainty into account, but we still have some data set on which doing this actually decrease the performance, and this is why ST is not the last model, because on some data set ST is actually achieving the best performance. Now, to summarize the strength of UST models, we see that UST is accurate, robust, and interpretable as all the existing shapelet algorithm, but additionally we have uncertainty taken into account during the classification process. And the main weaknesses is also something that have been inherited from shapelet time series classification with shapelet, which is the time complexity required to extract the top shapelet from the dataset. And this is in the order of ON squared times m to the power of 4, where n is the number of UTS and m is the length of our UTS. So the second contribution is about uncertain scalable and accurate subsequence transform. So here we are going to try to deal with this high complexity in order to accelerate the computation time of our algorithm. So why do we really need to do that? Why do we need to accelerate our algorithm? So the LSST project is the legacy survey of space and time. And the goals of this project, which is a ground-based telescope project, is to produce the largest and deepest images of the universe. This telescope can track about 37 billion objects, which are called transients at the same time. And these transients are actually objects that appear on space during a reduced time windows. So the time windows, you have a small time windows in order to observe the object and do the analysis. So, and this telescope generates 20 terabytes of data per night. So in order to apply our model on this data, we need to have a model that is more scalable. So to do that, we are going to take inspiration from psychology. So this image is used by Professor Eger to illustrate the invariance of recognition in our brain. So here we have different types of dogs. We have dogs in water, we have dogs we have drawings, we have photographs, we have different types of dogs, but our brain effortlessly says that these are dogs. And this is called core object recognition, this ability that our brain have to recognize any object despite substantial appearance in the substantial appearance variation. And from this, we want to define or to introduce what we call the core shapelet recognition, which is the ability of any shapelet algorithm to identify any shapelet despite any variation or substantial variation of the shape of the subsequence. And from this definition, we claim that assessing one or few instances by class of a shapelet is enough to do the classification, to find the best shapelet, and using a single time series should be enough also to do the classification or to find all the shapelet of the corresponding class. Additionally, we defined two hypotheses. The first one is that filtering shapelet candidates beforehand of classification could lead to inaccurate result in some situations, and also that the classifier is able to learn by itself the best shapelet in the dataset. So from that, we define our second model, a model which we call the scalable and accurate subsequence transform SAST, and the process is as follows. So given the dataset, we are going to perform some random selection of reference time series in the dataset. Ideally, we are going to select a single instance by class. Then we are going to generate all the subsequence from this reference time series and use this subsequence in order to transform our dataset as before, using Euclidean distance, then apply a supervised classifier to do the classification. If we are satisfied with the result of the classifier, we can then perform some feature analysis in order to extract or in order to see what are the best shapelet learned by the classifier. So to evaluate this model, we do 72 datasets from the literature. These datasets are already split in train and set, and it covers diverse types of problems. As competitor, we are going to compare ourselves to the state-of-the-art shapelet transform classifier. We also define a variant of this classifier, which is STCK, which use only K instance by class in order to do the class to find the top shapelet. Additionally, we compare to ALICE++, learn time series shapelet or LS, and also fast shapelet. We also come to compare our method to the state-of-the-art algorithm in time series classification, which are IFCode, Rocket, and TSCHIEF. Now, the first result I'm going to discuss is the STCK result. So here we compare the model in terms of accuracy using, as before, the critical difference diagram. So here we have consider four variants of STCK. The first one is STC1, which use a single instance by class in order to find the top shapelet. We also have STC 0.25, which use 25% of the time series by class in order to find the top shapelet. Similarly, we have STC 0.50 and STC 0.75. Then we have STC, which use the whole time dataset in order to find the top shapelet. So this is the classical shapelet transform classification algorithm. Now the result. So here we can see that there's no the difference between all the five models are significant, and we can see that the performance increase with the number of instances used by class to do the classification. So this is why we see that STC achieved the highest rank here, while STC1 achieved the lowest rank. And this may lead to think that using a single instance by class or a subset of instance by class is not good to do classification, but we see how this how the results are different with the SAST algorithm. Now here we compare SAST to STC, but also to STC1, and here we have the scatter plot showing the accuracy of both models in the same plot, and we can see that in terms of win-loss draw, SAST is better than STC. And something is interesting here to see is that on some datasets, which are the fungi dataset and the crop, our method achieve above 80% accuracy, while STC achieve lower than 20%. And we can see that fungi is a special dataset because it has a single instance by class in the training set. So it means that this configuration is actually a configuration where we have STC1. So even if you run STC on this dataset, you are actually running STC1, which is less accurate than the other method. But we can see that SAS is able to classify this dataset accurately. And in terms of significance, we see that SAS is ranked better than STC, but the difference is not that significant. So this is done by a test using a significance level of 5%. Now we compare SAS to other shapelet methods. So here we consider the 37 datasets used in the ALICE++ paper, and these are the results. We see that SAS is not better than ALICE++ in terms of in average, but it's not significantly worse than LS++. But something interesting to note here is that SAS is fully interpretable as the subsequent or the shapelet learned by the model are extracted from the training set. Whilst in LS++ and LS, the shapelet are learned using an optimization algorithm, and there is no guarantee that the learned shapelet will be interpretable by domain expert. So in terms of comparison to non-shapelet methods, here we consider 67 datasets for which results were published in the literature. And here in terms of average accuracy, we see that our method achieved 84% accuracy, while Rocket, IveCode, and TSCHIF, so this is IveCode version 1 because there have been some improvement. And we can see that Rocket, IveCode, and TSCHIF achieve 80% accuracy. So our model is less performant than the state-of-the-art model in terms of accuracy. And in terms of statistical difference, using the Wilcoxon sign rank test with a significance level of 5%, we find no difference among these 4 models. But with the same test using a significance level of 10%, we have some difference. And SAS is, in that situation, SAS is less performant than the state-of-the-art algorithm. So we also evaluate the scalability of our algorithm. We consider SASTEN, which is an ensemble of 3 SAST methods. We also consider SASTEN A, which is an ensemble of 3 approximated SAST. What I mean by approximated is that each model in our ensemble is focusing on a subset of the subsequent space. And what we see in terms of result is that in terms of the number of time series, our method is much more scalable than STC. And in terms of the length of our time series is the same, our method is much more scalable. For instance, if we consider a data set with 64 time series only, we see that SAS completed in 2 seconds, while STC completed in more than 700 seconds. So this is a speed up of about 36 times the computation time. So to summarize the strength of SAS, we see that SAS is accurate, robust, interpretable as STC. And we can see that the time complexity has been decreased from ON squared times M4 to ON M3. And this is a division of this computation time by a factor of O and M. In terms of weaknesses, we see that we can note that the reference time series could not be relevant in some situation. But luckily, during our experiment, we didn't find such a situation. And also, SAS is not as accurate as the SOTA. But at least we have the interpretability, which is highly important in some scenarios. So now that we have a scalable algorithm to classify shapelet in an interpretable way, we can find how to take into account uncertainty in this model. So we propagated uncertainty in SAS as we did with UST in order to propose the uncertain, scalable, and accurate subsequence transform, or simply said USAST. Additionally, we consider USAST-D, which is USAST in which we have removed duplicate subsequences from the set of subsequences to transform the dataset. We have also considered USAST-C, which is the USAST model in which we take into account the frequency of our subsequences. And we also have USAST-DC, which combines USAST-D and USAST-C in the same model. So now we are going to see the result of USAST on a real scenario. So plastic, which is the photometric LSST astronomical time series classification challenge, is a dataset extracted from the LSST project, which contains about 60,000 multivariate uncertain time series, each one with 6 dimensions, named after JRUIYZ, and the dataset has 14 classes, which are highly imbalanced. So here's an illustration of a sample extracted from this dataset, which actually represents a supernova. And here I have shown there's only 4 dimensions that are displayed. And you also have the result of imputing missing value in the time series. And here we only plot a single dimension. And the red region represents the uncertainty region, and the blue region represents the best estimate of the time series on this dimension. So in terms of result, so first we apply UST model on this dataset. And the result was that the method was not able to find any shapelet in the dataset. And we try to understand why, of course. And this is an explanation that we have. It's not a formal explanation, but at least it gives us some idea. So here you have two supernova of different classes, a supernova type 1ax and a supernova type 1a91bg. And what we see is that the right figure looks like a shifted version of the left figure. So if you try to search for a shapelet to differentiate between these two classes, it's going to be very difficult. And even in the even by discussing with domain experts, which are astrophysicists, they say that the classes in the dataset are actually difficult to differentiate because they have similar shape in common. So then we apply UST on the same dataset and we average the result over 3 runs to see if the reference time series used to do the classification were impacting the result negatively. So what we see is that the standard deviation of the result are generally 0.00 or 0.01. So meaning that the reference time series is not really a problem on this dataset at least. And in terms of result, we compute the precision, the recall, the F1 score, the loss of the model, and also the computation time. And we see that we can achieve above 70% of the precision, the recall, and the F1 score. And USAS-D is the model which achieve the best result compared to USAS or USAS-GC. Now, we also apply the SAST model on plastic, now ignoring uncertainty. So in this case, we can see that the performance actually degrades somehow, and this makes us think that taking into account the uncertainty in this dataset actually improve the performance. Now we compare USAST and the total algorithm on the same dataset. We compare to Muse, to Rocket, and to XEM. In terms of result, we see that Rocket actually achieved the highest performance, and it's also the fastest of the 4 models. But we see that SAS actually outperformed Muse and XEM a bit, and SAS is also the model that takes most time in order to finish. So the computation time in USAS is the big deal of the algorithm. But in terms of classification, we see that SAS is able to beat some state-of-the-art method. But what is also interesting with USAS is that we have the explainability, as I will show in the next slide, compared to Rocket, which is not explainable. XEM offers some explainability capability, but I will show you that XEM actually have some limitation in terms of explainability. So here is a local interpretability. So local interpretability means that we are trying to interpret only a single instance. So here the XEM model has been used to classify a sample from the dataset, and the XEM correctly classifies this dataset as being a core collapse supernova type 2, and also identify the most important region to be from 179 to 230, and this region is represented by the bold blue line on each dimension. What we can note here is that on dimension G, there is no signal at all in this region. Same for dimension U, dimension R, but we have signals on dimension I, Y, and Z. So we can see that although this region is actually the most important region, it's not the most important region for all the dimensions. It's the most important region for only 3 dimensions among 6. And we need to visualize the dataset in order to figure out that this was the case. So we do the same with our model, which is USAS, and here we do it on a supernova type 1a. You can see that the model correctly classified the object as being a supernova type 1a. It has also correctly identified the most important region and also the most important dimension, which is dimension Y. Similarly, we do the same with another object, which is a core collapse supernova type 2. The model correctly classified this object and correctly identified the most important region which contains the signal, and now the most important dimension is dimension U. So here we have shown only the most important shapelet, but we can also try to extract the 2 most important dimensions. So that's an advantage of USAS compared to XEM. And another advantage of USAS is that USAS can be used to have a global explainability of the process. So we can build for each class in our dataset a profile of most important subsequence that can be used by domain experts in order to do different tasks like discovering new objects or identifying anomalies in the data. So to conclude, so in this project we have been working on uncertain time series classification, and we have used uncertainty propagation and proposed the uncertain shapeless transform model, which is, to our knowledge, the first method for uncertain time series classification. Secondly, we have also introduced the core shaplet recognition, which we believe will be used in the coming years by researchers in order to propose new algorithm for time series classification with chiplet in a more scalable way. And we use it to propose our SAS method. And additionally, we've shown the effectiveness of our proposed method on not only simulated dataset, but also on real scenario. So as future directions, because this work has many limitations, we have, for instance, it would be interesting to improve uncertainty handling during the classification phase, because at the moment, the uncertainty handling at the last step of the process is not does not propagate uncertainty to the classes. So this is something that needs to be improved. And also it will be interesting to extend the models with additional ways of dealing with uncertainty. For instance, we are thinking about symbolic data analysis or interval data analysis techniques. It would be also interesting to extend our proposed method to situations where not only the input data are uncertain, but also the labels. And finally, of course, it will be interesting to tackle different tasks of uncertain time series analysis, like uncertain time series forecasting, uncertain time series clustering, and uncertain time series dimensionality reduction. So these are the main publications that we did during the thesis. The first one is about the UST model, which has been published at the International Conference in Data Mining Workshop. The second one is about SAS, and it has been presented at the French Conference on Machine Learning, and a journal version, an extended version is actually under revision at the journal. And also there's the paper on USAS, which have been submitted to a journal and is currently under review. So here are the source code of the 3 models that we proposed, which are available on my GitHub page. And I don't know if I have time for this, but here you have 2 videos of 2 transients, and maybe I can show you the tidal disruption one, if possible. No, excuse me. So a tidal disruption happens when a black hole, which is, you will see a black hole somewhere. So this is a black hole, and it's going to actually hit a star coming too close to the black hole. And this is what is called a tidal disruption. So this is a simulation from the SciTech Daily. Just an example. This is what happens when a black hole absorbs a star. So the star disappears after that. So these are the main references that we use during the thesis, and also here you have my GitHub page where you can have more information on the project I've been working on during the thesis. And that's all. Thank you for your attention. If you have any questions or comments, I'll be happy to take them.
So thank you very much for this concise presentation of your work. Maybe we should switch off YouTube because we have the next video in background.
And voila, we've got a Gantt chart. You can also set dependencies, adjust timelines, and change your colors too. And adding more tasks as this project progresses is not a problem.
Can stop this.
Consider this project managed. Access Gantt charts and so much more, and one app to replace them all. Click on.
Great, so we are now back to the set of questions. So your presentation was clear. It was didactic from my point of view, and you perfectly matched, in fact, the time constraints. It's very good. So we'll now start to assess your work with a set of questions by your peers. And the first set of questions will be asked by Professor Tony Banyard. Tony, can you hear us? Great. We hear you in the defense room, so you can start to ask some questions. Did you promote this?
Okay, so thank you for the question. So I know that there have been some work on using fuzzy logic in order to deal with uncertainty. And what I realized on this work is that the input data were not uncertain. So they were trying to take into account the uncertainty during the process, but not the situation where your input data, so when the data data provider gives you the data, they give you data with associated uncertainty. So many works I see on fuzzy logic, they were using, let's say, data without uncertainty, but trying to take into account the uncertainty during the decision process. And I would say that somehow there's a relationship, because I feel that fuzzy logic can actually be used in order to deal with the scenario that I described in my thesis. I don't know how at the moment, but I think that it can be useful, because we can use fuzzy logic in order to put some weight on different decision paths in order to deal with uncertainty. But I cannot give more detail on this now. It needs to be, I need to think about more to give more detail. Excuse me? Okay. So I think this word is actually a bit confusing, because sometimes I consider standard deviation as uncertainty. But I think this problem is coming actually from how we model uncertain information. Because in my thesis, I use the probability density-based functions, where I define an uncertain measure as a mean and a standard deviation. But actually, there are more information than that. We also need to have the distribution of the data in the interval. So going from the best estimate minus the standard deviation, and the best estimate plus the standard deviation. But I didn't really take into account the distribution of the data, because this is an information that is not generally provided by data collector. But in my work, you can assume that when I say standard deviation on an uncertainty point of view, this means actually that the value is somewhere around the best estimate, and the standard deviation is only used to put some boundary on how far we can move from the best estimate. I don't know if this answers your question. Yes, so that was a choice, I think, but so I explain this to my point of view. So I think that models like XCM or USAST or SAS, for instance, we have no guarantee that the learned shapelet will be actually subsequent. Let me give you, should be shapelet. Let me give you, let me show you this slide again, and you see what it means. So I think it's clear it's clear that the subsequence here on dimension G is not a shapelet. So this is why I think that even if we are classifying the data using subsequence from the training set, we are not sure that these subsequents are actually shapelet, as the shapelet should actually maximize the information gain. And on this dataset in particular, these subsequents ensure acting by all the instances in the dataset. So this is why I prefer to put XEM or SAST or USAST on a different categories that I called subsequence-based time series classification. So are you talking about yeah. Yeah. Okay. So in this simulation, I actually didn't try to estimate the uncertainty in the existing data, but I assumed that the data were clear without uncertainty, and I tried to add some noises in the data without assuming. So they are generated randomly just for simulation. The problem of that is that so when I read about paper on uncertain time series classification or uncertainty in time series analysis in general, generally the author doesn't publish their dataset. So it was difficult for me to find an existing dataset on which I have uncertainty. So I follow a similar process as they do in their paper and try to add some noises in and let's say a certain dataset. So that's what I do during this experiment. But I agree with you that the dataset on the literature have some uncertainty because any measure is subject to uncertainty, but I didn't try to actually estimate this uncertainty. Yeah. So maybe for that we can use conformal learning to, I don't know, maybe using conformal learning we can try to come up with some estimate of the uncertainty in the data set. I don't know. Okay, so if I get your question is when I was using a contract to limit the computation time and when I wasn't using this contract, right? Okay, so for the scalability experiment, I didn't use the contract. So I run the algorithm by enumerating all the subsequents and without using a contract. But for the classification or the accuracy, I use a contract to limit this. So this is because I didn't do the experiment at the same times. Because I obtained the result on the classification performance, and after that I tried to compute the scalability of the algorithm, but I couldn't do it if I have defined some contract because I wanted to see the real time complexity of the algorithm. So when I was experimenting on the scalability of the method, I didn't define the time contract. So this one. Yeah, I think it's because of the phase. Because in SAST, since we are using all the subsequents, we are somehow keeping so because the subsequents used in SAST are not really phase independent, even if they are phase independent in the sense that when we are computing the similarity between a subsequent and a time series, we don't really take into account the phase. But since we are using all the subsequents, I think somehow we are able to find out if we combine this subsequence with another subsequence and another subsequence, then maybe we can find a way to distinguish between two classes. But with chiplet transform, since we have to do a shapelet of a selection of the top shapelet before classification, the classifier doesn't have this information. But with SAS, we are using all the subsequent, so the classifier can learn that by combining different set of subsequents, even if they do not have a high information gain, they are actually good together to distinguish between classes. So this is the hypothesis that we have to explain why SAS actually is able to classify this dataset, while with STC we have a failure. Okay. Thank you very much, sir.
Thank you very much, Tony. Now we will have the question from Sébastien Dester, Research Director at the University of Compiègne. Can you hear us, Sébastien? Thank you. Yes, great.
Thank you. Okay, so thank you for the question. So I know there are different view of uncertainty. So maybe I should put it somehow more clearer. Is that in my case, I assume that the process of collecting the data provides me data that are uncertain. So my input data are uncertain, but the process of performing the classification is not uncertain. As when you have a supernova in the space, you have a supernova. You know that it's a supernova, but so the problem is that I started actually working on this project during my internship, my master internship, and I read the book from Taylor, and in that book, consider actually I received the interval point of view of modeling uncertainty. But even in the same book, when they try to take into account the distribution of the data, they start using a probabilistic view in order to, let's say, to compress the length of the interval. So in that way, they combine both view of uncertainty without giving more discretion on how to combine these two. but they use it to reduce the length of the interval. And concerning UDBN, is that I was just looking for some classifier used to deal with uncertain data. And it comes out that in the literature, we have some classifier that takes interval data as input. And this classifier doesn't really take into account the distribution in the interval, but only that the input feature are intervals. And since after the transformation of my data, I have the best estimate and the standard deviation, I could actually convert these to interval and use this classifier. But if I was able to find some classifier in the literature that was actually taken into as input an uncertain measure, which is let's say a best estimate, a standard deviation, and a distribution, I will have used this method instead of UDBN. And actually, UDBN, I think, have some limitation because UDBN doesn't propagate uncertainty. So they assume that the interval follows Gaussian distribution, and they use the best estimate only to estimate the mean of the distribution, and the length of the interval only to estimate the standard deviation of the Gaussian distribution. And I think that this is actually a limit in their approach, but this at the time was the only solution that I have in hand to do the classification while taking into account the uncertainty. Yeah. Yeah, I agree. Okay. Yeah. Okay, so I have an application in mind. This is a project on which I am working actually. And in this project, they have time series. Their time series are not uncertain. But the problem is that they are using many sensors in order to measure the same value actually. So normally the same this all these sensors should measure the same value, but it happened that the value measured by this sensor are completely different. So you have different value representing the same variables and you don't know which value is the correct one. And I don't know, I think that in this case using an interval will be limiting because you are how to say it, maybe if you have a single variable you can maybe use an interval that contains all the value and you have maybe a fairly big interval. But in this situation I think this actually naturally fits in the case where multi-set based model is better because we will know that all these measures that we are using in our decision process are measured by at least one sensors. But if we use interval, we will have some value in the intervals that were not actually measured by a sensor, and this can bring more problem than solution. I guess I think this is a situation where multi-set based model will be better, at least in terms of classification performance. Yeah. Mhm. Yeah, I think it could be an issue in some situation because actually when I computed the UEG for some dataset, there were cases where I have the best estimate be or no the uncertainty being too large, so that when you do the best estimate minus the uncertainty, you obtain a negative value. And in this case, it's an issue if I use interval value in order to do the classification. But I don't know if in a classifier point of view, because I input the best estimate and the standard deviation, but I don't actually compute the interval. So I give it to the classifier like the best estimate and the standard deviation, which are both positive values. But I agree that if you compute the interval, the real interval, you will obtain some negative value. And I think this is why I think this is why after the propagation, I didn't actually compute the interval, but instead I input to the classifier the best estimate and the standard deviation. So if you have lots of, if you compute the intervals and you have a lot of negative values, I think that will be very problematic because we have negative distance and we will need to do the classification on it. But I cannot say that it will give poor result in terms of classification because maybe even if the value are negative, in terms of so let's say we are projecting our data in another space, even if the value are negative, maybe this projection actually leads to something that is easier to separate by the classifier. So even if in theory it's wrong, but maybe in practice this can actually lead to something that is good in terms of classification. But I didn't try.
Yes, you have time. Don't worry, we have time. It's just 17 past 3, no problem.
Yeah. So, so thank you for this question. So I think that keeping the uncertainty from the beginning to the end of process is for me the ideal way to do to deal with this kind of applications because our data are uncertain. So probably maybe we have some instances in the data set that are also uncertain. So we cannot only say that this data is from one of the classes. So we need to have this information, we need to give this information to the end users that even if we think that we strongly believe that this object is in this class, we have some uncertainty that will say that maybe it's actually in the other class. So this is one advantage that I think we have by keeping the uncertainty from the beginning to the end of the process. Now it comes with also some difficulty like the computations, because we need more computation. It also comes with the problem of decision at the end, because if we give something that is uncertain to the end users, it means that it will require, let's say, more thought in order to decide what to do on the information. So that are, I think, the main limitations. So in my case, it's true that with the ordering, I actually make the uncertainty disappear, but this is only temporal, because after the ordering, I still keep the uncertain measure after the ordering. The ordering is just to decide which one is more important or which one is the minimum. But after that, I keep propagating the uncertainty to the next step of the process. And now I agree with you is that in the classification step, if I'm not using UDBN, for instance, or even if I am using UDBN, I'm not propagating uncertainty to the classes. But this is one of the perspective, and I think it will be really interesting to have this information, especially in this case where we know that our classes are extremely difficult to differentiate. So maybe by having this information, we'll discover that there are some maybe labeling problem on the dataset. So that's why I think doing this is actually interesting, even if it brings some additional difficulty in the process. Yeah. Yeah. So, so let me think a little about it. So by defining some boundaries around the shape, you will have. I think it's quite similar to what is done here using standard deviation or using probability-based representation. But the thing is that we have the fact that the uncertainty is different at each time step. So it means that even if we define a boundary, we are not saying that each point can be, no, let's say each uncertainty region is the same value for each point. So I don't know if this is the situation you are describing, is that we have our subsequence and we say, okay, we can remove, let's say 5 or add 5 to the value in order to have our uncertainty region. So it means that we have the same uncertainty at each time step in our subsequence. Am I right? Yeah, okay. Okay. So this situation is actually what is done so this similarity measure, which is called dust, in which they did actually this assumption. And I was thinking that this actually limits somehow the the analysis, because does assume that the uncertainty is the same at each time step. So you have a single value of the uncertainty for a single time series. But in my case, I want to have the uncertainty at each time step. So I think this is more flexible and includes what is assumed in dust. And as I show in the result, you see that our method is actually more accurate than when we use dust here. And I think this is a problem because here, even if we added simulated uncertainty in the data set, for dust we have to decide which value we will use as uncertainty for every time step given a single time series, and we actually choose the maximal value in the interval. And we think that this is a limit because we cannot be flexible. Maybe today the sensor is highly accurate, and tomorrow something happened, the measure value is less accurate, and tomorrow again is more accurate. So we want to take this into account during the analysis. Yeah, that's right. Yeah. Yeah, I think so. I will start by answering the question about the potential advantage of treating of being more multidimensional. So in this application in particular, there are some relationships between the dimensions. So depending on the distance between the object and the telescope, some dimension will have the signals while the other one will not have the signals. And this is due to something called the Doppler effect. I cannot give more detail on it, but that was told to me by domain experts. And I think yes, in this case, if we can treat the dimension, let's say at the same times, taking into account the dependencies between the dimension, we could, why not even reducing the computation time by removing some computation that are not needed. And now the question is how can we do that? This is the question. I think in the literature there are some strategies in order to deal with multivariate time series, and a nice way will be to find for a single subsequence we try to find if it's a shapelet on all the dimensions at the same time, and this will bring more computation. Or you can try to find multivariate shapelet or multivariate subsequence. And in this case, we are trying to map each dimension of our shapelet with the corresponding dimension in the data. I don't know if this will bring a good result, but what I know is that there is a state-of-the-art algorithm on time series classification and multivariate time series classification published recently that says that actually the best result were obtained using a good method on each dimension separately. So, but maybe this is because we have not found a good way for now to deal with the multiple dimension. But at least at the moment, this state-of-the-art paper says that if we use a good method on each dimension separately and then combine the prediction, then we have the better result. This is the result that is published in the literature. Yeah, I think yes, this could actually be interesting because when we face this problem, we try to apply the algorithm on only two classes, and we were able to identify some classes that were easier to classify than others. And but this was actually let's say empirical because we had to try any pair of class sequentially in order to find that okay, these two classes are easier to separate. But if we have a clustering algorithm that can deal with uncertain time series like this, then we can apply a clustering algorithm, an uncertain clustering algorithm to the data set and have a subset of the data set on which we can build a single classifier that will be normally easier for the classifier to learn the separation. Yeah, I think this idea could actually work on this application. Yeah, exactly. Thank you. Thank you.
Thanks very much, Sebastian. I will give the mic to Elisa Froment, professor at the University of Rennes. She will ask the next set of questions. Yes, great.
Okay. Yes, sure. Thank you for the question. So, I don't know if I can be of a great help here because I think that to do that, it's really application specific. For instance, in this situation, they use some formula used in physics in order to estimate the uncertainty on their data. And to do that, they have to model the clouds, they have to model the rotation, they have to model the light in the space, many things, in order to estimate the uncertainty on their data. And in a situation where you are using sensors, some things, let's say maybe naive, will be to have different sensors measuring the same value and try to compute, let's say, a distribution of the value and use this as a measure of the uncertainty. But this is really naive because it's also depend of the precision on the sensor, it's depend of the environment, it's depend of the situation in which they are making the measurements, and it's application specific, and this need to be a discussion between the people collecting the data and the domain expert to define what is actually interesting for them to measure as uncertainty. So I don't think if I can be of big help here, but if I have the situation in front of me, maybe I can have more insight. But it's really application specific. So most of the applications that I found up to here are in astrophysics because they have a lot of uncertainty and they actually take care of it, even if the existing models that they have, even in astrophysics, machine learning model doesn't actually take into account the uncertainty. So when I presented this work to astrophysicists, they were really happy to have a method that actually take this into account. And I think a situation where this can be used, even if we don't have the uncertainty on the input data, is when we have a lot of missing value in the data set. We can actually input the missing value in the data set while adding some information on the uncertainty on this input value. For instance, if we use Gaussian processes in order to estimate the missing value, Gaussian processes give us the, let's say, the mean and an standard deviation, which we can use as uncertainty in order to give maybe more important to value that were in the original data than to value that were input to the imputation model. So I think this is a situation where we can actually take this and as a way to add uncertainty on the value we are inputting in the dataset. But otherwise, I don't have other application at hand where I have input the uncertainty. Yeah. So good questions. So maybe I will go with XEM because it's more scalable. Yeah. I think I have because there are some interesting properties in XCM that I actually wanted to use in SAS in order to accelerate the computation because we have a source of free and we can use some subsampling of the features in order to reduce the search space. And by combining bagging and boosting, I think I can actually do two things. So I can improve the accuracy of the model, but also have this scalability problem solved at some level. So maybe I will use it because it's explainable, and I will find a way to come out with the explainability by dimension, not only all the dimension in the dataset. That is something that I could do. I also wanted to go with Rocket, but with Rocket, since they're using random features, I will miss the interpretability, even if I have, let's say, a good scalability and a good classification accuracy. But the idea can be actually translated easily to the Rocket algorithm for sure. So if I had to start from the beginning, I think maybe I'll give a few times trying to see what I can do with XEM and Rocket. But this will be actually a few times because with Chaplet, I can actually find some idea to improve the SAS computation time. For instance, using techniques that have been used in Rocket by randomly picking some subsequence in the subsequent space, for instance. So that's why I think I will do, but I will not give too much time on exploring XEM or Rocket because I know that explainability might be a big issue at the end. Yeah. 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 Exactly. I would say so. Actually, no. For the moment, no, because I didn't work a lot on multivariate time series classification. Maybe by working more on the topic, I will find some ways to deal with that, to find some cross-dimensional chaplet or multivariate chaplet. I don't know how, because in this situation, for instance, we know that the most important region is not the same when we change the dimension. But in some situation, it could be the same. If it's the case, if you have a scenario where the most important dimension or the most important region is the same across all the dimension, then we don't really have the exponential scalability issue. In that case, we can use the same algorithm, but that we define multi-dimensional chaplet, and we assume that, and we do the sliding windows on all the dimensions at the same time to compute the similarity. This is something we can do in this type of scenario. But if you have scenarios like this, that the one we have here in astrophysics, where the dimensions, the importance of a dimension varies, then I don't know how we can deal with that at the moment. Yeah, maybe this can be true in some scenario, but in this scenario in particular for the astrophysics, when you have no signal, it means that there's nothing. So you cannot really count on this information to do classification, because you have this let's say for instance this subsequence, you have it here, you have it here, and if I take another example here, you have it here, you have it on all the instances in the dataset. So you cannot say that this is actually something that, if the model is using this to do the decision, is a wrong feature in a domain expert point of view. But I agree that in order to optimize the classification accuracy or the lost functions, these actually appear to be a good features. But when we do the analysis afterwards, we see that for the expert, we don't have to count on this information to do the decision, to decide. Yeah. Okay. Yeah. I see what you mean. Yeah, I see. I see what you mean. I see what you mean here. Yeah. Yeah. Mm-hmm. Yeah. Yeah. I agree. I agree. The things was that, so here you have 6 dimensions, so it was actually is easier for a human to visualize and see that, oh well, maybe it's because we have nothing on the dimension J and something on dimension Y that we can say that this is a core collapse supernova type 2. But if you have what I was trying to do with users is that we can come out with the same information, but gradually we can look at the first dimension, then the second one, then the third one, and so forth, in order to have something that is not the same, but something that is similar to what we have here. So that was the main point, is that we have, if you have, so here we have 6 dimensions, but if you have more than 6, we still need to visualize all these, or to find combination of the explanation to say that, okay, this is why the model is classifying it as this class. But yeah, I agree with you. If we can, I think that for the classifier, it's important to see that nothing is happening here and something is happening here. And this is something that in their application, depending on the distance between the object and the telescope, we can have such a situation. Yeah. So it's about 6,000 UTS of length 261. Yeah. Yeah. Views rocket, yeah, yeah, yeah. I agree. Yeah. Thank you for the questions.
Thanks very much, Elisa. I will now give the mic to Denis Palpanas, professor at the Institut Universitaire de France.
Yeah. Mm. Okay, so just to make sure that I have understood the question was, the first one is to see so is what happens when the uncertainty on X is actually larger than the uncertainty on Y, even X is smaller than Y. Am I right? Okay, so this is something that could happen actually in practice, and we are aware of that. But the thing is that we think that we want to give more trust on the best estimate because this value is given by domain expert. So even if the uncertainty on X, yeah. Yeah. Mm-hmm. Mm-hmm. Yeah. Okay. It's yeah. Yeah, I agree. I agree because the uncertainty on y is smaller than the uncertainty on x, so we can assume that y is more certain than x. Yeah. Yeah. Mhm. Mm. Mm, yeah, I think it's an open problem because so in the manuscript we try three types of ordering, and in terms of classification performance, we see that the difference between the ordering, so the impact of the ordering method was not too big on the classification performance. But maybe this is because maybe this is due to how we add uncertainty in the dataset. And this actually, I think, is an open problem. Here we define some properties in order to work with, but I'm not aware of a way to order on certain measures with properties that are good enough or that are better to the one we have here for the classification purpose. I'm not aware of that. So the three one we tried in the manuscript were so we tried something based on the CDF, and we also have this simple ordering and another ordering based on interval data that have been proposed in the literature. And these simple orderings actually was the one that were in the data set that we try on, were giving the best classification result at the end. But I'm not aware of an ordering strategy for uncertain measures that is good, that is better to this one for the classification purpose. That's why we use this one in the thesis. Yeah. Yeah. Mhm. Yeah. 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 That's right. Okay, so you are right because to measure the performance of the classification, we use certain value. That is correct, and this is one of the future direction that I mentioned in the end of the presentation, because the classifier that we use so at the end of the process does not give uncertainty on the classification. They just give the prediction as classical classifiers. So we use this to measure the performance of the method, but we think that in the future we will need to have uncertain predictions and then define some uncertain metrics in order to or find a way to compute let's say an uncertain accuracy or an uncertain precision in order to compare the performance of these models. But we didn't have time to tackle this problem during the thesis. And concerning the uncertain moving average, we didn't try that. I think when I read the paper when I read the paper, I thought that the metrics that were presented mostly in the paper were Munich, Prout, and Dust. So I don't know why, but probably I forgot about the uncertain moving average metrics, and this is the reason why I didn't compare to this metric. I didn't compare to Munich and Prout because they are probabilistic measures, and I couldn't find a way to use probabilistic measures in order to come out with uncertain chiplet or to perform uncertain chiplet transform. Yeah. Mm-hmm. Mm-hmm. Yeah. Okay. 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 So that's an interesting question. So we use Gaussian noises because it turns out that Gaussian noise is appear in many applications. So we thought that this will be a good distribution to use for our comparison, and this is also the distribution that have been used in the yeah, I think it's mentioned in some papers that Gaussian distribution is it's more it's highly present in different applications. But I'm not saying that we don't have to try other distribution. It's important to try other noise because we never really know the distribution on the noise in advance. I agree, but in our work we have only tried Gaussian noise. In every timestamp in the plastic dataset, you have an estimate, a best estimate, and a standard deviation. You have no idea on the distribution, and you don't have multiple samples for the same timestamp. And this is why we didn't try to use the multiset based representation, as the dataset is actually modeled as a best estimate and a standard deviation for each timestamp. Yeah. So I think there's a great debate in the literature to define what it means to be an explainable method or a white box method or a method that can be adopted by domain expert. And I don't have the truth on this definition, but for me, explainability is how can I see inside my model? How can I explain? No, I won't use explain here. It's for me, it's how can I understand why my model is giving me a prediction? This is what I want to come out with. And in image classification, generally they come out with the most important pixels in the input images to explain the predictions. And similarly, in time series, we try to come out with the most important timestamp or the most important subsequence in the time series classification. And this is the type of explainability that I use in my work. But if you use other approaches like interval based classification of time series, the most generally explainability is about extracting the most important intervals. And so in my case, I use the most important subsequence, and I extract this subsequence in the case of SAS using the N classifier, which was a decision tree. So I use the nodes with the highest information gain as the most important node, and the associated features or the associated subsequence is used as the important subsequence in the input time series. So this is how I extract the explainability. You mean what you mean? I think I mentioned it on the chapter on the scalable and accurate subsequence transform when I was talking about the explainability. Yeah. Okay, yeah, I understand. Yeah. Okay, thank you.
Thank you very much, Professor. Now I will give the floor and not the mic because Professor Engelbert is present in the defense room.
Oh.
So, Engelbert is also the supervisor of Michael's thesis. Now it's your turn.
It's my turn. Okay, so what can I say? I will not ask question to Michael. I think we have spent a lot of time during these 3 years debating about your thesis and discussing about all these topics. First of all, I would like to thank all the members of the committee for agreeing to be in the Michael thesis and to be here this afternoon. And for Michael, just to say that it was a great pleasure for me to spend all these 3 years and a half working with you. And I would like to congratulate you for all this great work that you have done. And I would say that it's mainly, I just give you 2 words, uncertainty and time theory, because you were coming just after the thesis of Vanel, CU, about uncertainty and clustering. And then one of our interests was about this data set, because we were just starting a project with the physicist, and then you say, okay, let's go and start working on classification with uncertainty. Because before that, I think we were thinking when we start thinking about your thesis, about working on graph. And then at the end, we just switch to time series. Yeah. And I would say that, in fact, all of the ideas that are in your thesis are mainly your idea. Okay? So you are a very good hard worker and very autonomous on what you have done during these 3 years and a half, and I appreciate too much to spend all the time discussing with you.
Thank you, sir.
And what I can say is just to wish you good luck for your next career or work, and maybe I hope that in the very short term you will be in the taking a position in the university to start also trying to also to show to students what you have learned. Okay.
Thank you, sir.
That's what I can say.
Thanks very much, Engelbert. So now I have to give the floor to myself. I've been impressed by your presentation, and as your former teacher, I'm really proud of what you have achieved, in fact. I already gave my comments about your written report, and now, even if I'm not specialized in your domain, I have many questions as an examiner, in fact. So I will try to perceive what kind of insight you were able to acquire during this thesis work. And since the beginning of your thesis, you are aware of the importance of reproducible research. From my point of view, you know that this aspect is not addressed in many research work, not really in your presentation, though you've done huge efforts to give the artifact to others. ACM proposed recently in 2020 a change, new definitions, in fact, to differentiate between repeatability, reproducibility, and replicability. I have seen all the links you give in your thesis, in your presentation, and can you say what kind of documentation in code you have put in place so that other scientists will take it to word and come to the same scientific conclusion?
Okay, thank you for the question about. So I'm a bit aware of reproducibility, as you said, because I did a classes during my master internship on the topic, and I always try to give all the information that I needed to reproduce my code. And all my code are on GitHub, and documentation are generally written on a written page. So once you open the page, you have the documentation in front of you. And on the documentation, you have the dependencies. So what are the libraries that I use to build my code? You also have how to install the dependencies, how to rerun the experiment, how to download the dataset, and also you also have a description of the content of the repository. So this is what I generally put in the documentation in order to help other people reuse my research. And also I also put my contact details, so if there's any problem, I can be contacted by other people wanting to try my research to help them.
So from my point of view, this is a real input for science advance that could be added at the end when you present your main contributions. Because there are so many work without all the job you did for the other to be able to reproduce. Can you put back the slide where precisely you present your major contributions?
So the conclusion?
Yeah. Maybe just before the conclusion. Okay, so if I look at this, another strong contribution of your work, and I think it's also an input of your work compared to, for instance, SOTA, you should have added explainability as a contribution, because it's a real important contribution.
Yeah.
If we make science advance and cannot explain, you know this better than me because you are scientists in AI. So there is no strong theoretical background for everything. Even in computer science, we have limited theory, in fact. But it's a strong contribution that you have done by your technique. Maybe it's difficult to compare with everything, but when you compare, you can go back to the weaknesses maybe of UST and strengths.
Okay.
Go back to this. The slide where you compare this. I do not remember, sorry, I was typing and not noting the slide numbers. Accurate, robust, scalable, etc. But you say not as accurate as SOTA, but as strengths, I would add the explainability. Am I right or not?
Yeah, I think you are right.
Okay, and for me it's a very strong point. So you should have this when you have to sell your research papers to journals, etc.
Okay.
Compared to what the other do, in fact. Third set of questions, dealing with uncertainties with AI. I'm sure it's really exciting. For me, I tackle this because I'm doing simulation with random sources, etc. So we have to deal with this, not for AI, not for training, but what I've noticed, in fact, is that since 2016, many researchers have produced adversarial examples with small random noise, invisible to the eye, very confusing for artificial neural networks, and they give inconsistent response. For instance, an AI may confuse a turtle with a machine gun, completely different, or a stop sign with a priority. That's very bad for automatic driving.
Yeah.
Another point for automatic driving, the same kind of problem you have with a telescope is in snowy weather like this morning, where we have a little frost on the windshield, we still see correctly and we can drive.
Mm-hmm.
And AI can't, in fact. And I've noticed even that some random noisy images of cars or traffic lights were proposed by the OpenAI ChatGPT when you log in, for instance. They check that you are human. There's a smart captcha, because they are based on this noise and images to be sure that you're not a robot with machine learning capabilities. So the problem that we find with images is the same with many dimensions, for instance with sound. And do you think that your approach, UST, would be a kind of antidote dealing with uncertainty? So scientists could propose or limit or eradicate this kind of problem that we encounter since 2016 where adversarial examples were crafted with small random noises?
Okay, good questions, because actually it has been shown that time series classification methods are highly impacted by adversarial examples, and this even if you are using deep learning or classical machine learning algorithm for time series classification. And I will not say that my approach is an antidote to that problem, but I feel that it's a beginning of a solution, because one of the properties we wanted to have was the robustness, because we want our model to work even in the presence of high uncertainty. And if we are able to model this uncertainty in applications such as image classification, computer visions, or any other situation, maybe we build models that are more robust to these situations. And I know in network security, generally we build more robust cipher, and then people come out with more robust, I don't know if I will say decipher. But if you have more robust model, maybe people will come up with more robust adversarial examples, and we end up entering in a cycle of perpetual improvement. So it might not be a solution for now, but it's a starting point. We need to take this uncertainty into account to deal with such situation. And being able to do that will actually lead us to models that are more robust and more trustable also, because we'll be able to deal with the uncertain input.
Thank you. After all your work, in fact, you think that uncertain shapelets can be used to improve the accuracy, the efficiency of time series when compared, of classification, in fact, when compared to other classification algorithms. I think this is why you proposed in your these kind of approaches. Of course, the problem is to compare with many other approaches. I've found some, but not always. In fact, from my limited knowledge, there are a number of algorithms that can be used for the classification of uncertain time series. And I want to understand where you place yourself, in fact. So you cite the dynamic time warping, sometimes in combination with the k nearest neighbors, KNN, also sometimes combined with support vector machines to improve the accuracy of time support classifications. And shapelets are in this area, in fact. But there are also hidden Markov models, and I've not found this kind of approach in geodesics. In fact, HMM, they can be, of course, particularly useful when you model time series data, but also when you have variation of or noise, they are useful. And another point is also deep learning with the CNN, convolutional neural networks, and also the long short-term memory networks. Yeah. And I've not seen this quoted as well, LSTM, not quoted in your thesis as well. So how can your proposal compare or be placed if I have to go for a classification? I understand that you cannot compare with everything, but maybe you should. Yeah. Because it's better to propose your approach and to compare it with the other techniques, the other algorithms that are good at classifying uncertain time series.
Yeah, good questions. So there have been a lot of state of the I would say review papers on time series classification methods, and it comes out that when we take into account deep learning approaches, we take into account LSTM, convolutional neural network, we take into account dynamic time warping. We see that meta ensemble like IveCode or Rocket, which use random convolution, or TST are actually the best method, even compared to deep learning method. So these methods are good because they are able to extract different types of features. And in IveCode, we have features that have been designed, I will say, by the human somehow. And in Rocket, we have random features extracted using random convolution. And so maybe I was biased by this review paper, and I tried to use the method that were stated to be the most accurate in the literature. So this is why I didn't compare to LSTM, to
the hidden Markov models.
Yeah, exactly, because in the literature,
DTW with SVM or KNN.
For instance, for DTW, it has been shown that using local features is better than using global features, like what is done in DTW. And also DTW have this problem of scalability because the time complexity is above n squared. So there are many reasons like that which can justify why I decide to go to compare to IVE code, to Rocket, to test because they are known to be the most accurate method in the field of time series classification. And how is my model compared to this one? I need to do the test first, but if I look at the result that I have compared to IVE code, and this is the first version of IVE code. There is another version which is even more accurate than the first version, significantly more accurate. So if I compare to the second version of IVE code will beat my approach dramatically. And if I look at the Rocket result, which is actually this, I would say the second most accurate method in parentheses, not sure because it needs to be verified. I would say that compared to other methods, I wouldn't be too far from them because Rocket is actually better than these methods if I refer to the comparison that have been done in the state of the art. So I think I wouldn't be too far off them in terms of accuracy. But in terms of interpretability, I'm not sure that these methods are interpretable at all.
So this is why it is a strong point of your work. So if I understand, you have a certain shaped transform that has been used to handle multidimensional time series with LSST. Am I right or not?
Uncertain.
To handle multidimensional time series.
Yeah.
You address this.
Yeah.
Okay. So can we use your approach for multidimensional time series such as video or audio sequences?
Yeah. If you have them represented as regular time series, you can use the method. So if I have my videos and I am able to extract some features from the video in order to represent it as time series, maybe they are signals, maybe they are something else, we can use the approach, that's for sure. But that is always the question. If you have a time series of graph, how do you convert your graph to numerical features in order to have time series of numerical value? So if you manage to do that, then you can use the approach to do the classification.
Thank you. Can you integrate UST with other time series analysis techniques such as clustering or anomaly detection, or to improve the overall performance of these algorithms?
So that's one of the perspectives, and the idea is that the arithmetics used to propagate uncertainty are mathematics. So I think that they can be applied in any other scenario. But now the question will be how to do it from the beginning to the end of the process and how to do the computation. That will be the difficulty. And to answer this question, I need to see exactly how the computation is done in this particular application in order to see how we can propagate uncertainty. But I think that is not impossible because it's only mathematics that mathematical formula that are applied.
Thank you. So do you think UST could be used to identify or to forecast patterns in streaming time series in real time?
Interesting questions. So there have been a work from a former PhD student from the University of Versailles, I think, about streaming time series. And in that case, there were no uncertainty at all, but they have streaming time series and they wanted to learn shapelet in real time. And I think that in this approach, we can actually use uncertainty propagation in order to learn uncertain shapelet in real time and do streaming time series classification, for instance, or streaming time series anomaly detection. So I think, yes, it is possible to use the ideas introduced in this work to do online learning.
Thanks very much. Now it's more general. In fact, when a code is too long or too complex, we face in computer science the undecipherability problem, and machine learning at the part of the computer science field is also undecipherable. In fact. So, are you aware of theoretical work dealing with this subject to improve the application rules that could be used when you propose a new algorithm or classification tool? Sorry.
Not very much, but it's always good to find some properties of let's say of convergence to know in advance if the algorithm is going to learn what we want it to learn. In my case, I have no idea of that. I don't have such properties. This is why we need to run UST to see that it will give us no shape that has been found. because we don't have properties to guarantee if the model, or to guarantee in which conditions our model will work or not. So in my case, I don't have that, but that's a property that will be interesting to identify. And I am not even sure if they exist for every model.
I understand. And I think by working on explainability, you did a step towards this, to be able to have more theory, to give a framework. Where can we use this approach? Where can we use the other approach, to give advices like we do in operation research or in other fields where know that problems are intractable. So again, explainability of what you did is a very strong point. Maybe another remark, maybe more than a question. I'm from the stochastic descriptive and simulation field, as you know, and I will deal with a question that Professor Palpanas raised. In fact, I would add some insight. In fact, the Gaussian or normal distribution is just one example of probability distribution that you can use to describe noise. You can also use uniform distribution, Poisson distribution, and maybe exponential distribution to model a kind of disorder. The choice of the distribution will depend on the characteristics of the noise you are modeling. So it could be, as he said, how do you know? Do you observe the distribution to see if there was a symmetry? Because it will be used if the noise you find is symmetrical and has a constant variance. Otherwise, and this is my opinion maybe for LSST, the Poisson distribution will be used to model noise that is random in fact and has not a fixed rate. So what do you think about this, about LSST? Am I wrong? Maybe you've got symmetrical noise data?
I think this should be discussed with the domain expert, but so I asked them the question about the distribution of their uncertainties, and they were thinking about Gaussian noise. That's what they think about, but without any proof or any formal proof that they are following a Gaussian noise. So I don't know. Maybe using this distribution will be better to model the uncertainty on this data set.
And if you look at the distribution, because you've got enough data, you find the distribution, you do a key to test, and then with this test, you know what kind of distribution it is, in fact. It could be really easy to find.
Yeah, but I didn't did this experiment, so I just take their word as a Gaussian and try to go with it.
Okay. Thanks very much for all your replies. It was a pleasure for me to ask questions.
Thank you, sir.
And we will now have to leave to deliberate, and then we'll come back with our value.
Okay, thank you, sir.
So, for yeah, let's switch to the other link, the first link for the committee. Ok.
Monsieur, vous restez là ou...
On bouge et on revient.
Ah, ok, d'accord.
On va dans la salle de délibération et on revient. Vous pouvez rester, tout le monde peut rester, et nous on bouge, on revient comme ça, vous n'avez pas... Merci pour les cacahuètes, il reste à nous. C'est gentil. Le prof qu'on va pas manger. On va le débrancher du mur, c'est branché du mur, parce que sinon, ça arrive de faire tomber d'autres personnes. Le temps que je revienne, c'est plus sûr. A tout de suite.
Non, pas encore. Faut attendre. L'installation, tu es là?
Oui, c'est ça. Oui, je suis là, jusqu'au week-end.
Ok, pas de soucis. Je passerai discuter de certaines questions.
Tu ne me dis pas que tu as aussi des questions. Je vais poser toutes les questions. Je vais poser toutes les questions. Je vais poser toutes les questions. Est-ce que tu vas encore demander?
Je vais te peut-être, moi je n'ai pas tout compris. Les autres ont tout compris.
Ok, ça marche.
Je passerai peut-être demain, mais ensuite.
Ok.
Ok, c'est là que je viens pas mal. Ouais, ils ont tout en fait j'ai aussi pris comme ça. Et il y a une collègue qui est
Même le doctorat là. Tu as la foutaise. Ça va changer.
Comment?
C'est le j'ai acheté plus de 10 ans.
Il faut qu'on
10.
Ah oui,
comme ça.
ok, ouais, c'est pas mal.
Si j'ai acheté, c'est la troisième.
Ok.
Normalement, de connecter, c'est tout.
Sauf que moi, je dis, c'est différent.
C'est deux soirs.
C'est vrai.
Mais peut-être tu prends quand même ton dossier quand tu... Je sais pas. C'est pas mal, je ne comprends pas très bien comment ça fonctionne.
Au moins, ça les direct.
Mais sinon, ah sinon pour le début. Ouais, je suis parti au moment des questions. Ouais, j'en prenais beaucoup, mais t'as défini à quelle heure? Parce qu'après, j'avais. Ah ouais, parce qu'après, j'étais pas revenu pour pas te déranger dans la mission.
Je vais dire section sur YouTube. Ils attendent la délibération. Bah, ils savent.
Apparemment, sur YouTube, ils n'entendent pas les questions des gens qui sont sur silence. On n'entend rien.
Ah.
Bon, c'est pas grave.
Désolé. C'est bizarre que ça, ils m'entendent, mais pas les questions.
Ah, bah tiens,
Non, les questions, les entendent.
Ouais.
Je sais ça, ouais.
Ils sont tous partis sauf Doctrin.
Ouais. Le doctrine, il était censé venir et il m'a dit qu'il allait du coup, les qui m'ont.
Ouais. Ibrahim était là ou pas?
Ah, je sais pas. Tu veux voir les photos? Je me dis, genre, ça se met, ça se rapprochait plus. Là, c'est là, elle est même. Mais là, tu vois. Là, tu regardes de l'autre côté. Comme si tu regardais. Ah, ça va être trop bien. Moi, ce que j'aime bien, c'est ça. Ouais, genre, quand c'était des promos sur ça, mais je crois qu'ils ont fait ça. Je pense qu'ils ont fait une seconde de c'est là, et j'avais aussi. En fait, quand il était éloigné, ça c'était un peu, je rapprochais. Et ça, j'aime bien. Là, du coup, tu disais ta contribution. Là, tu regardais vraiment le jury, du coup, j'essayais de te prendre en photo.
Quand il fallait compter les trucs, je pouvais pas les regarder.
C'est vrai, c'est vrai.
Mais là, je crois qu'il y avait des affiches.
Alors, je fais là.
Hello. Yes. Hello.
Ils sont toujours.
Oui, ça va. Yeah, thank you, thank you. Where are you? Ah, okay. Okay, I understand. We are just waiting for the result. Yeah, I hope so. I hope so. Yeah.
L'enfant a bien que vous avez bien content de ton travail. Vous avez bien discuté. Vous avez parlé de moi aussi.
Moi-même, c'est là que je suis voilà, c'est bon. Ouais.
C'est en train de diffuser sur l'écran.
Ouais.
Et depuis qu'on dit qu'on ne peut pas aller, genre, tu t'es dit que toi, tu sais, à chaque fois qu'on a une économie, tu joues comme ça.
Quand tu vois la famille.
On va gérer ça.
Ils sont pas sûrs de te le donner.
Toi, tu sais. On va gérer ça. Non.
Parce qu'en fait, moi j'étais arrivée et justement j'avais un peu un mal parce que j'étais en train de tout ça. Et il y avait le micro-là qui me dit bon, heureusement tu me connais parce que sinon je pense qu'il n'aurait pas été sûr.
Mais ça serait pas gratuit le week-end là-bas.
Un jour.
comme c'est la gratuit, c'est là.
Moi, je n'ai pas les questions qu'on entend. J'aurais enregistré.
Parce que je sais pas, c'est juste que là, du coup, moi, si jamais je fais la sapiens, peut-être la même chose que toi.
Peut-être j'aurais dû mettre studio. C'est mieux studio. Je crois que ça va réussir à casser chacun de la maison. Ça m'envoie mon sur YouTube.
Ok.
Ça va sur mon c'est divers juste pour faire ça.
Ouais, mais après, peut-être que par exemple, je sais pas, mais si tu peux transférer le son de Teams vers
Comment ça va marcher?
Doc? Doc? Doctor?
Non, ça on n'entend pas. Parce que ça capture le micro.
Ouais, mais je veux dire, c'est par exemple, moi je prends mon téléphone, je prends mon YouTube, est-ce que moi j'entends ta voix de plus en plus?
C'est pas si pas que ce soit ça va suffire.
Ah,
Tu t'entends pas. Si tu entendais ça, mais il faut avoir
Il faut prendre le
Je suis d'accord.
mais sur le mon montage, j'avais ce dessus, mais je vais laisser ensemble.
Oui, parce qu'en fait, j'avais mis ça.
Et du coup, sur Teams, c'est indépendant de musique. Ouais, du coup, sur Teams, en fait, ils ne voyaient pas.
Je me voyais avec
Ouais, mais on te voyait ça. Ouais, on te voyait au début, en fait, on te
tu me vois.
Ah oui.
C'est vrai, si je suis avec ça,
Ouais, parce qu'en fait, ce qui a été mis en tout cas pour vous, c'est que ça devait être c'est trop tard, on ne sait pas, mais on met la caméra comme ça, de façon plus claire, de voir.
je crois que c'est ça. Mais c'est moi
En fait, c'est moi, parce que moi, je nous arrête. Et j'ai aussi, la carte du jeu avec la tête. Ok, je ne peux pas me connecter. Parce qu'ils m'ont dit, je dois faire ça.
mais il faut vraiment pas parler de la question.
Ouais, je pense. Parce que ce que Véron, enfin, comment je parlais avec Véron, il m'avait dit qu'elle t'entendait toi. Donc, du coup, c'était toi qui mais par contre, elle n'était pas de question de. Et du coup, c'est Ok.
C'est pas obligatoire.
Je pense que c'est parce qu'il y a c'est qui va aider la
Aline s'est blessée. Ah bon? C'est blessé mercredi. Donc elle y allait pour faire les autres. Et elle est tombée contre des filles qui étaient chez elle. Ça va faire le 4. En bas, elle m'a dit qu'elle faisait 5. Mais elle a dit 4. Donc elle a fait le 4. Le 4, c'est un PT. Ouais, c'est un PT. Et elle a fait une yoga en 4. Donc elle voulait faire des poussées super bien. Elle était ceinture bleue, c'est sûr. J'étais un peu dégoûté qu'on a dit de moins pour la ceinture rouge. Littéralement, il lui en a parlé en plus, on peut pas savoir. Et en c'est la même qu'elle marche. C'est facile. Et donc, il y avait Pierre et Marion qui m'avaient dit mais c'était parce que je pensais qu'Aman les avait vus. Ils sont passés. Mais c'est ce que tu aurais expliqué. Je vois en plus, même les trucs bizarres, voilà, ça a changé les choses, mais ça renvoie à sur les championnats du monde, pour aller au championnat de France, ils vont quand même passer pour les régions. Voilà, est-ce qu'ils vont aller au aussi, tous ceux qui sont là, parce qu'autrement, il ne voulait pas l'envoyer choisir. C'est le seul qui a eu une médaille.
Ah, parfois, oui. Parfois, oui.
C'est les médailles, il ne voulait pas l'envoyer.
Obligation de résultat.
Il faut les connecter là, ils sont connectés. C'est plus mettre plutôt l'image, plutôt. Et le serment que tu as préparé, tu dois prêter serment en anglais. Peut-être après. Après, quand on te donne le titre de l'auteur, tu as le serment en anglais. Pardon?
J'ai vu que c'était obligatoire de prêter serment.
Comme tu veux, tu peux ne pas prêter serment si tu veux. Après, nous on coche, n'a pas prêté serment. Vous savez, il y a une feuille comme ça. So thank you, we are now all together, and it was a pleasure to hear your defense, Mr. Michael Wobda. You were clear, you were consistent, and you were perfectly matching the time constraint. We have noted your didactic and pedagogical datasets. You have made a smart use of appropriate illustrations to present your work. You also addressed important questions dealing with uncertainty, handling in machine learning, and in general for time series classification. It's an important area that is still unexplored, and you have brought different contributions to this field with simulated data sets, but also with real scenario in astrophysics, the domain where uncertainty is preponderant. So you replied to all our numerous and challenging questions. You have convinced the PhD board that you have a broad and deep knowledge of your research field. And the PhD board has been impressed by your original contributions and the result you reported during the defense. And we unanimously acknowledge that you deserve the title of Doctor en Informatique de l'Université Clermont-Auvergne. Congratulations. I will let you, the PhD board, congratulate you. So maybe we try to make a picture with the wall of all our heads. So please activate your video camera if you can, all of you, because I think there will be some pictures. So we will stay in front of the, maybe around there, if you can come.
Ici c'est bon, je suis là.
Ici, it's okay? Okay, it's okay.
Ouais, c'est bon.
Okay,
ça on est partagé sur les deux côtés.
If Elisa and you can activate your camera again. And okay. Are we all there? Yes, I think we are all there now. So if you want to take pictures, you will have all the PhD board, distant PhD board, and also the local one.
1, 2, 3, cheese! Okay, 1, 2, 3, cheese!
Thank you very much. Thank you very much. Congratulations again, and you can go back and see
okay.
family.
Thank you.
Bon.
Il y avait Sophie connectée.
C'est toi de parler.
C'est à toi de dire, de remercier le jury.
Remercie.
Tu peux lire, oui, si tu veux.
There is a, vas-y, lis.
Tu peux lire, lis.
Vas-y, à ton tour.
Lis,
On fera qu'on coche.
Okay. Okay. In the presence of my peers, with the completion of my doctorate in computer sciences, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. And I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, to my methods, and to my results.
Congratulations again. Thank you, Tony. Thank you, Sebastian. Thank you, Elisa. Thank you, Dennis.
Yeah,
Thanks all of you for being there distantly.
Thanks to everyone. Thanks for accepting to be a member of my jury. Thank you for coming to the presentation. Thank you, everyone.
Thank you. Bye-bye. You have to say something. You have to say something.
So I think I've been speaking since 2 p.m. So
Thanks to the jury.
okay. So first of all, I want to thank you again, all the members of the jury. I want to thank all my friends who have managed to come to the presentation, either physically or remotely or via YouTube, because I am also live streaming the presentation on YouTube. And a big thanks to my family, to my girlfriend, and to my little boy, which is now 2 months year old. And yeah, so it's been a long journey starting the PhD. I was very excited when I started, and I managed to propose some contribution to the research field, and I hope that I will continue to that way, and that this will be also a starting work for other researchers who will come after my part. So big thank you to everyone. Thank you, Elisa. Thank you, Sebastian. Yeah. Me too.
Bye-bye. Bye-bye.
Okay.
I love you.
Bye-bye. Bye-bye. Bye-bye, Tony. Bye-bye, Sebastian. Bye-bye, Elisa.
Okay, so we are going to share some sweets, some drinks on the next room. So if you are remote, take a cup of coffee or a cup of wine and drink it with us. And for the other one who are here, let's go to the next room.